it's only one potential function
Okay.
for a gradient, for a vector field. Not all vector fields have a corresponding potential function.
Okay, but there will only be one.
There will be more, specifically one, and we'll find it. I'm sorry, does someone have their hand up?
I was just complaining.
Well, I mean,
Again?
differentiating, we can still lose constants and get the same gradient.
Say that again, I'm sorry, I just didn't catch that.
Because we're differentiating, we can still have constants and just lose them and get the same gradient. I mean, it's just like with integration, like, you have the arbitrary constant when you integrate because. So, I mean, it's only,
Yeah.
there's no difference in the
I agree.
actual curvature of, surfaces, but, or curves. But, you can still have several different curves.
That's true, because if it is the case that my function phi looks like this, if it's a function of two variables, but it's set equal to some constant called c, then I get various different level curves, or in 3-space, maybe level surfaces. Sometimes you refer to those level curves and level surfaces as equipotential curves and equipotential surfaces. And they always have the quality that they're orthogonal to the corresponding vector field.
Okay. One other thing is, what special traits are there to conservative vector fields? I'm just curious because otherwise we really wouldn't care if they didn't do anything special or had something that made them useful.
And the utility for you and I is if we're working with a vector field, and all of a sudden I find out it's conservative, it's going to allow me to evaluate some integrals so much more easily than cranking up by brute force. And the reason being is I'm going to prove to you, generate a corresponding new second fundamental theorem of calculus that's allow us to use these potential functions to easily evaluate some line integrals.
And you said integrals of, I assume, vector spaces?
Vector fields.
Oh, yeah, vector spaces. Yeah, vector spaces.
Completely different. Yeah.
Yeah, vector spaces.
You mean conservative by like physics, like non-conservative stuff?
Well, maybe in physics when you talk about conservative vector fields. But I'm not talking about conservation of energy.
Okay. So it's just a term.
Yeah, you treat this as a man-made definition of it. A vector field is simply conservative if you can go out there and find a corresponding potential function whose gradient vector is equal to your vector field.
Oh, what is it conservative to with what?
Well, no, it's not to anything. A vector field is conservative if you can go out there and find some scalar value function phi.
Can you give an example of that? Maybe that would be.
Yeah, that's the example right there. See how I gave you a scalar value function?
Right,
Now, look what happened when I created the corresponding vector field.
right.
Then I will say that this vector field right here in my big box is conservative. Because there exists a function phi, this one right here, whose gradient vector is my vector
So
field.
because you can differentiate the first,
Yes.
then it's conservative.
Yes.
Oh, differentiate the second also?
Well, didn't I differentiate with respect to x and then respect to y?
Okay, so differentiate with respect to each partial of the original function. If you get an answer, then it's conservative.
It's just you and I are going to go backwards, Linda.
Show
It
us one
allows-
that's not, because I'm not seeing why,
Oh, yeah.
yeah, show us one
Well,
that's.
okay, first things first though. Understand that this really is kind of backwards. What would be really slick is I started off with this vector field. And if I have a technique for generating that function field there in thin air, then I'll be able to complain that this is a conservative vector field. How could I not want? What if he gives us bounds by which it doesn't exist?
So it has to be bounded within an area.
Oh, I'm not saying, but you could do something like that.
Gradient field, it seems like every gradient field should have a phi, right?
Well, absolutely. It's just that not every vector field, you'll be able to generate that field in thin air. That's the issue.
What if
So
we
my-
can't generate because we're just dumb?
That's a good point. And we're going to get to the situation where we can't. And so we're just going to evaluate whatever integrals I come up with by brute force.
It seems like a weird kind of test. Anyway, sorry.
If we're gonna have 14.2 on the test, you might wanna get to it.
Well, can you show us a quick example of one that is not conservative?
Well, it's not that I want to show you an example where one's not conservative. I want to show you examples where it's too difficult to find the scalar value function.
Okay.
To me, that's the issue. And I'll do that when I hit that thing called the fundamental theorem of line integrals.
Okay.
We'll get there. Speaking of line integrals, you guys, I know this is a really kind of a loose discussion today with vector fields because, technically speaking, with most vector fields, let's just easy ones like I gave you as examples today, I do need you to generate those vector fields. But I just want you to know what they are, how to navigate through them, et cetera, et cetera.
So is that something we need to know for the test?
Say that one more time.
Are we just kind of talking about it a little bit, or are we having this on the test, or?
It's going to be on the test, but the questions are going to be as easy as the questions you see in the homework tonight. They're going to be very straightforward. Look at this picture, tell me what's going on.
We're going to generate an equation from a graph of a vector field.
Not yet.
Are we gonna have,
In the near future, what I'm going to have you do is look at some curves or even some surfaces in the vector field and talk about what's going on.
are line integrals gonna be on the test?
I don't know. Let's see how it goes today.
Okay.
So you guys, here's what I want to do next. For a brief moment, I want you to just focus your attention on the x-y coordinate plane. Do not go up the z-axis. And I want you to just talk about a curve sitting right here in the x-y coordinate plane. And I want you to build a fence.
Ooh, like the cover of the book.
Yeah, you're right. It is just like the cover of the text, isn't it?
Yep.
I'm going to develop a technique that essentially computes, I don't know, how much paint I need to paint one side of the fence. I don't want to deal with my neighbors. And the way I'm going to do it is by creating a line integral. The line integral is what's going to allow me to evaluate the area of one side of that surface in 3 space. The notation I use is a little bit different. I will use the integral symbol, but I typically put a C underneath it. Eric. He didn't say anything, that's good, thank you.
I was still drawing the picture.
The integral symbol, and I have a C below it describing the curve. Now, the way I evaluate these line integrals is I'm simply going to compute, how about this? Can I talk about a function C? I think the integrand's position. I've got my function F. And I'm going to evaluate at those points along the curve C. And I'm going to integrate with respect to, gosh darn, I'm stuck. Yeah, I think instead of integrating with respect to x or y, I'm going to integrate with respect to s. Now, I got to confess, you guys saw earlier this semester that I can reinterpret that as nothing more than the magnitude of r bar prime t. Then integrate with respect to t. But I think I can also take this line integral and parameterize in terms of x. And if I do, I've got an x prime of t dt. Or maybe I can do it in terms of y. I also think I can interpret this as nothing more than a line integral of some function f evaluated x comma y. I can actually integrate with respect to x. In addition, integrate with respect to y. And when I use this kind of notation, write my line integral this way, I am not making any mistakes. It is the case that I do not use parentheses when I integrate with respect to both those variables. Now today in class, I'm simply going to try to come up with a couple examples where we're simply evaluating line integrals along curves. Oh, you guys, yeah, there.
I'm assuming that integral is supposed to transfer all the way throughout, so it's between C and where, or you have region C for both of them? Because you only drew it once, so.
Say it again, I missed it, I'm sorry.
Integral on one, integral on the other. I'm assuming it goes all the way through.
Yeah, that's what I'm saying, it looks like awkward notation. It looks like I should have parentheses around the entire thing.
Yeah.
But the way we denote this line integrals, we do not involve these parentheses. We do not do that's, I know, it's a very different type of notation. Eric, this really comes into play because I'm integrating with respect to 2 different variables.
Okay.
So that integral's applying to both sides.
Yes, it is. Everything that is beyond the integral symbol really is the integrand's position.
How would you indicate the end of it?
Say that again.
How would you indicate like the end of the integral if you're gonna write it down?
It's just understood as notation.
Okay.
Suppose could you put parentheses on the outside of the integral on both sides?
It's just bad notation. I mean, the reason why I like the parentheses is when I have everything within the dx or the dy. I mean, that to me makes sense. It's
Right.
just that we don't put it around the entire integrand when it comes to line integrals.
Are you just too lazy to write it as two separate ones?
Or is that?
Or is it?
You know, you could put it that way, you're right. I agree. I agree. Here's my x-axis, here's my y-axis. Consider the points 1, 1. Hold on, you guys, I want to think for a minute. Oh, jeepers. How about 2, 4? Here's C1. Here's C2. Here's C3. Notice that with each and every one of these curves, they start at the same point 1, 1. They terminate at the same point 2, 4. It's just that they get there differently. What I want you guys to do is evaluate the line integral if I'm really looking at the curve C1. Now to do that, I need to parameterize appropriately. So, do you guys remember reading in the text something I don't think I discussed on how to come up with a parametric representation of a line segment? If here's my x-axis, here's my y-axis. If I got an r sub naught bar, and maybe this r sub 1 bar, do you guys at least remember how I created equations of lines in vector form? Didn't it look just like this? R bar t was equal to my initial vector r sub naught r, plus, I don't know, a v bar times t, where v bar was simply my direction vector. Did you really?
Yeah, we did that.
In what class?
In physics.
Oh, cool.
Yeah, to determine which one has the least amount of work associated with it.
Yes. Yes, I agree completely. We're going to be doing the same thing. Okay? But you guys, let me take a break and let's just talk about line segments. And if I got a line segment from this position, this point in T-space to this one, then I think what I could do is think of r bar t representing the line segment. I think I can have that as an r sub naught bar plus v bar times t. It's just that v bar is my direction vector. Look at my picture. Can't I think of that direction vector as this? Or shall I say the following? R bar t representing the line segment is simply going to be my r sub naught bar plus r sub 1 bar minus r sub naught bar times t. Or allow me to rewrite. Doesn't it just become a 1 minus t?
Wait. Shouldn't you distribute the t through, so shouldn't the r sub 1 bar be multiplied by t as well?
Thank you very much. I really did miss that. I'm missing my factor t. You guys, can we see if I made a mistake? You know, if I evaluate this vector value function at t being equal to 0, what do I get? R sub naught bar.
Oh, yeah.
And if I evaluate r bar t at t equals, how about 1? The whole first term drops out. What's left over? R sub 1 bar. So I think if you want a vector value description of a line segment, this is how you do it, where t so conveniently ranges from 0 to 1. So I think of my picture over here. If I want a vector value representation of C1, oh, it'll be a piece of cake. With C1, what's the initial vector? I couldn't hear that. 1, 1. What about R1? Yeah, wasn't 2, 4. That being the case, I think r bar t representing my line segment is simply going to be, well, 1 minus t times my 1 comma 1 plus my r bar 1 times my t. But doesn't just become the following? 1 minus t comma 1 minus t plus, is that a 2t 4t? Or shall I finally say, I've got a vector valued function that is going to be represented as a, can you guys help me with, is that a t plus 1, comma, is that a 3t plus 1? For values of t range from 0 to 1. So in vector form, I've just described how to generate my C1. You guys think that was a lot of work? Yeah, I thought it was way too much work. I never do this. I just come to class showing you guys what the author of text does, or what he says. So can I show you what I do? Because I'm just too tired. I simply come in and say this. For that here C1, notice how x can be generated. Just by looking at an initial value of positive 1, that's my first x value. And if I want to go all the way to 2, I'll simply add t once. Because now when t is equal to 0 and 1, I get the point, the positions 1, 2, respectively. I play the same game with my y values. I know I'm starting at 1. It's just that when t is equal to 1, I'm going to get a 4. Isn't that an increase of 3 units? So I just add 3t to it. I hope it's the same answer. Oh, you guys look, it's the exact same thing. So I came up with a vector representation of that line segment, just by hand, not by going through the little formula. Although I proved the formula to you, it doesn't t for it.
Wait. So,
Why is t range from 0 to 1?
Ah, here's why. Because over here, if I allow t to be equal to 0, notice I've only got the vector r bar. It's a not. When t is equal to 1, I get r sub 1 bar.
So it's always,
So if ever you want to create an equation of a line and list this vector value representation from 0 to 1, you've got those two vectors r sub naught and r sub 1.
okay, so t always ranges 0.
wait.
Yes, using this technique, t will always range to 0.
Wait, so what did you do again? You looked at t and you said, or x.
I'm just saying, look at all the work I just did in these two boards. I think it's nonsense. I don't go through any of this garbage. I just create the equations by hand, just like that, out of thin air. My initial x value is 1, so I got a positive 1 here. My terminal x value is going to be 2, so I want to add 1 to it. Well, I can do that by adding t if t is going to range from 0 to 1.
Well, that sounds nice and neat for C1, but what about C2?
Well, that's different. I didn't say it in words, but I wanted C2 to be part of a parabola. It's not a line segment. I just didn't get there yet, so I didn't use those words.
Oh, okay.
So my technique for evaluating line integral is going to be completely different.
Yeah, that's what I'm saying, so.
So just for C1, let's evaluate.
C3 is pretty much the same thing, except it's just 2 different
Well,
integral
C3 is going to be a lot easier, because again, I can't draw very well. I meant C3 to be the result of adding a horizontal and a vertical vector together.
Yeah.
So my line's going to be really easy. So you guys check this out. If I'm going to express this line integral as something I can actually compute along the curve C1, here's what I'm going to do. I got an integral as t ranges from 0 to 1. Oh shoot, it's math 30 business. I guess another name for y is 3t plus 1. What's another name for dx in terms of dt? dt. Plus my x, which has another name of t plus 1. Times my dy, but another name for dy in terms of dt is. But I guess as a single integral, bless you, that's simply going to give me is that a 6t, you guys, plus, bless you, is that a 4? I'm just struggling with my arithmetic. That evaluates to a 3t squared plus 4t as t ranges from 0 to 1. Or shall I just simply say, nice clean number, 7. That's the evaluation of my line integral. Okay, what does that give me? You can think of this as some event structure for which I'm looking at the area on the surface of one side. You guys, I'm being really goofy when I say that. When I evaluate line integral, that's usually not what I'm after. I'm after something in terms of applications. It's just my first day discussion of line integrals. I just want a nice, clean, easy geometric interpretation of what the heck is doing. That's when I talk about being excited.
So with respect to C1, what is 7 represent?
Well,
Basically, that's just the amount of work it's gonna take to go across that path. Isn't that what we're pretty much
that
what we're figuring out?
my first application is we're gonna think of this the amount of work traveling through some vector field described by this business up here. I got it.
So all we're doing is comparing the three ways we could go and which one's gonna be the lowest amount.
But I admit it's jumping ahead of me a little bit. You guys, I know I'm out of time, we're not gonna finish this, but let's just set it up. Second question. Let's see if we can evaluate this line integral over C2. Well, I think this one single integral becomes a following. You guys, I didn't say this, but I want C2 to be the standard parabola of y equals x squared. So another name for y in terms of x is
Yes, good.
x squared. And I got a dx. But another name for dy, if y is equal to x squared, is, or shall I say, I've got an integral of an x, is that a 3x squared? I made it with respect to x. Oh, but shoot, in this parabola, how do the x value range? Well, x starts at 1 and ends at. Shoot, I'm integrating with respect to x. So I'm just looking at extreme values for x to create that curve C2. Oh, shoot, you guys, this 2 is an absolute piece of cake, isn't it? Is that going to be an x cubed ranging from 1 to 2? Or shall I just simply say 7? I have evaluated my line integral.
Really quick, that's not the argmax, right? As you're going through that.
Quite the contrary. And when I'm using this letter C, I'm really talking about a curve sitting right down here in the xy value. Now, I confess, when you look at the r bar prime at t, when you look at my first definition, that resorts back down. You guys, I'm out of time. Can somebody on Wednesday, could you just remind me what this example is? I made it about thin air. So we can actually look what happens when we're going over the next curve C3. Oh, there's something else before I erase everything. Is that the same answer I got before?
Yeah.
What? That's the same answer I got before?
Yeah.
Really?
I don't think it was.
It was a 7.
Yeah.
Man, I'm so upset. That's supposed to happen. In general, I think the evaluation of these line integrals, it depends on the path they take. But I made this up out of thin air. I just got lucky. We will study what happens when it's always evaluates the same line integral, the same value.
Then it's path independent.
Then it's path independent. We're going to have a lot to say about it. I think my first example will not be path independent. I'll tell you what. So you guys practice.
So,
Line integrals on the
this
exam?
is gonna be on the exam, that's what we really want to.
As of now, I am not sending that exam to the printers. So 14.2 will not be on the exam.
Okay, so everything through
Can you guys
14.
just take a peek at these?
One.
please?
Just say yes to the
No
14.2 is
14.2.
No longer on the exam.
No longer on the
Well, I can't. I only gave you one exam. Well, 1.5.
But 14.1 will be on the exam?
Yeah, and you guys, if you and I smoothly, if you just allow me to come to class, if you allow me to just talk one section a day, which is not bad, we will have no crunching at the end of the semester. I know I missed a couple days, and that really is supposed to hurt. But if you just allow me to cover one section a day, that means we're going to finish things comfortably, not letting me cram things down your throat going into the final.
Can we set things up in a way so we don't have any new stuff that we're learning on the final week?
I'll have to check.
Is there any way we could do that?
I'll check.
All right. It'd be a lot, very
So,
helpful.
can you guys have the 14.1? Take a peek at the following. Seven through 17, all. Twenty-one, 24. Twenty-five to 33 all. 34 through 36. Paul? You guys, can you just make sure you read ahead of me? I really wasn't happy this weekend when I actually did my homework. I went through section 14.2. It's a really big section. He throws a lot of stuff in there that he's not using yet. I'm gonna do my best not to change the organization of the chapter. I will do what he's doing, but there's a lot in there, so please give it a solid read before you come to class. The exam on Friday, you guys are free to go through live. I know I'm late. The exam on Friday officially covers sections
13.6 and 14.1. Well, Maddie said 13's always right, so.
I mean, that's what you guys-
13.6 to 14.1, that would be awesome.
No, 13.3
Okay, well, that's what I.
over 14.1. In other words, you guys, it's an exam on immigration.
Of course.
Well, we math 31.
-1.